Hello. Is anyone there?
By the mid-19th century, industrial societies were expanding faster than their ability to communicate. Cities were growing, businesses were operating across regions, and governments were managing increasingly complex systems. Yet long-distance communication remained slow and indirect. Letters depended on railways and ships. Urgent messages required physical transport, which introduced delays measured in days or weeks. Even within cities, coordination relied heavily on messengers and written notes. The human voice, the most natural and efficient carrier of meaning, could not travel beyond shouting distance. The telegraph, introduced earlier in the century, represented a major breakthrough. Electrical signals could travel instantly over wires, shrinking distance in unprecedented ways. However, this system came with inherent limitations. Messages were encoded in Morse code, which required trained operators at both ends. Communication was symbolic rather than natural. Emotion, tone, and nuance were stripped away. Errors were common, interpretation varied, and the system was inaccessible to the general public. Most people could not directly use the telegraph without intermediaries. As commerce accelerated, these limitations became more visible. Businesses needed rapid clarification, negotiation, and coordination. Railways required precise scheduling. Newspapers depended on fast, accurate information. Yet the telegraph could not fully satisfy these needs. It was efficient for short, factual messages, but poorly suited to complex human interaction. The gap between how people naturally communicated and how technology allowed them to communicate was widening. This gap defined the problem space into which the telephone would eventually emerge. By the 1860s and 1870s, telegraph networks were dense and heavily used. In many regions, the problem was no longer whether messages could be sent, but how many could be sent over limited infrastructure. Telegraph companies faced congestion. Each wire could carry only one message at a time, forcing companies to lay more lines or find ways to increase capacity. This challenge drove intense technical experimentation. One proposed solution was harmonic telegraphy, a system designed to send multiple messages simultaneously over a single wire using different frequencies. Engineers and inventors across Europe and North America worked on this problem. It was within this context that Alexander Graham Bell began his own experiments. Bell was not initially trying to transmit speech. Like many others, he was focused on improving telegraph efficiency. However, these efforts revealed something important. Electrical currents could be varied continuously, not just turned on and off. If a current could change smoothly in response to sound vibrations, it might be possible to transmit more than coded pulses. This idea challenged the prevailing assumption that electrical communication had to be symbolic. Still, most engineers viewed voice transmission as impractical or unnecessary. The telegraph industry was profitable, entrenched, and skeptical of radical change. The bottleneck was conceptual as much as technical. The telegraph had shaped expectations about what electrical communication should be. Few people were asking whether a completely different approach, direct voice transmission, might be possible or useful. Bell's work would challenge these assumptions by reframing the problem not as message density, but as human usability. The idea of transmitting the human voice electrically was not entirely new, but it was widely regarded as unrealistic. Voice is complex, consisting of continuous waves with varying frequencies and amplitudes. Many scientists believed that such complexity could not be reproduced accurately over wires. Others questioned the need. Why transmit voice when written messages worked well enough? Bell approached the problem differently. His background in acoustics and speech shaped his thinking. He understood sound as a physical phenomenon, vibrations that could be measured, analyzed, and replicated. To Bell, speech was not mysterious, it was mechanical. If sound waves could move air, they could also modulate an electrical current. This perspective reframed voice transmission as an engineering challenge rather than a conceptual impossibility. Crucially, Bell's focus was not on replacing the telegraph, but on enabling a new form of communication. Voice transmission eliminated the need for coding and decoding. It allowed immediate clarification and natural interaction. Anyone who could speak could use it. This shift promised to democratize long-distance communication. Still, skepticism remained strong. Investors doubted commercial viability. Scientists questioned reliability. Telegraph companies saw little incentive to disrupt their own business models. The telephone was not an obvious improvement. It was a departure. Its value lay not in efficiency alone, but in changing how humans interacted across distance. Recognizing that value required seeing communication as a human system, not just a technical one. When the telephone was first demonstrated in the 1870s, its significance was not immediately obvious to everyone. Early devices were crude, range was limited, and sound quality was inconsistent. Yet the underlying principle worked. Speech could be transmitted electrically and understood at the other end. This alone marked a fundamental breakthrough. Adoption followed a familiar pattern in technological history. Initial use was experimental and localized, then practical applications emerged. Businesses realized they could resolve issues in minutes rather than days. Doctors, newspapers, and rail operators found direct voice communication invaluable. Telephone exchanges transformed individual devices into networks, multiplying usefulness exponentially. As infrastructure expanded, costs dropped, and reliability improved. What began as a technical curiosity became essential urban infrastructure. Over time, the telephone reshaped social expectations. Immediate communication became normal. Distance lost much of its practical meaning. Decision-making accelerated, coordination improved, and personal relationships changed. The ultimate success of the telephone lay in alignment with human behavior. It did not ask people to learn a new language or code. It adapted technology to natural speech rather than forcing speech to adapt to technology. Bell's contribution was not simply inventing a device, but demonstrating that electrical systems could serve human interaction directly. By solving a problem rooted in everyday experience, the telephone became one of the most transformative inventions of the modern world. Its success was not sudden or accidental. It was the logical outcome of recognizing that communication technology had to match how people actually think, speak, and live. Alexander Graham Bell was born on March 3, 1847, in Edinburgh, Scotland, into a family where sound, speech, and communication were not abstract ideas, but daily concerns. His father, Alexander Melville Bell, was a respected authority on elocution and speech correction, best known for developing visible speech, a system designed to teach pronunciation by representing speech sounds visually. Bell's mother, Eliza Grace Simmons Bell, was a skilled musician who gradually lost her hearing, an experience that deeply shaped Bell's sensitivity to sound and communication. This household environment exposed Bell early to the mechanics of speech rather than to engineering or industry. Dinner table conversations often revolved around articulation, hearing, and the physics of sound. Unlike many inventors whose interests were sparked by machines or factories, Bell's curiosity grew from human limitations: how people speak, how they hear, and what happens when those processes fail. His mother's deafness was especially influential. Bell learned to communicate with her by speaking clearly, slowly, and directly into her ear, developing an intuitive understanding of vibration and resonance long before encountering formal scientific theory. Bell was not considered an exceptional child by conventional academic standards. He was curious, observant, and imaginative, but not disciplined in rote learning. His strengths lay in exploration rather than memorization. This distinction would later define his approach to invention. Bell did not begin with equations or blueprints, but with close observation of human behavior and physical phenomena. Bell's formal education was irregular and unconventional. He attended several schools in Scotland and England, but he did not excel in standardized curricula. Subjects like classical languages and mathematics failed to hold his attention. Instead, he gravitated toward experiments with sound, music, and mechanics, often conducted independently rather than as assigned coursework. In his teenage years, Bell assisted his father in teaching elocution, including working with students who had speech impairments. This early teaching experience sharpened his analytical skills. Explaining speech required breaking it into components: breath, vibration, articulation, and understanding how small changes produced large effects. Bell learned to think in systems rather than isolated facts, a habit that later proved critical when designing complex devices. The Bell family relocated to Canada in 1870 following the deaths of Alexander's two brothers from tuberculosis. The move was motivated by health concerns and marked a turning point. In the quieter environment of Ontario, Bell had greater freedom to experiment. He constructed mechanical devices, explored musical instruments, and continued studying sound behavior informally. Soon afterward, Bell moved to the United States, where he found work as a teacher of the deaf. Unlike many inventors of the industrial age, Bell never trained as an engineer. His education was rooted in physiology, acoustics, and pedagogy. This non-traditional background allowed him to approach technical problems without being constrained by established assumptions in electrical engineering. Bell's professional life before the telephone was centered on education, not invention. He taught at institutions for the deaf in Boston and worked privately with students. His methods emphasized oral communication rather than sign language, a controversial stance at the time, but one consistent with his belief in speech as a physical process that could be trained and restored. Teaching required patience, experimentation, and close observation. Bell studied how students produced sounds, where they struggled, and how vibration could be sensed even without hearing. These experiences reinforced a key insight. Sound is fundamentally mechanical. If it could be felt, measured, and reproduced physically, it could potentially be transmitted through other media. Financially, Bell's teaching work provided modest stability but little wealth. He lived simply, balancing instruction with private experimentation. Importantly, this work connected him with a network of scientists, educators, and patrons interested in communication and hearing science. These connections later proved valuable when Bell began seeking support for his experimental work. Bell's professional identity during this period was that of a teacher and speech specialist, not an inventor. This distinction mattered. He did not pursue invention for prestige or competition, but as a natural extension of his work with sound and communication. The telephone emerged from this context not as a sudden career shift, but as an extension of existing concerns. Bell's personal life provided stability during a period of intense intellectual development. In 1877, he married Mabel Gardiner Hubbard, one of his former students, who had lost her hearing in childhood due to illness. Their relationship was built on shared experience rather than dependency. Mabel was intelligent, independent, and deeply supportive of Bell's work. Marriage brought Bell emotional grounding and financial support. Mabel's family, particularly her father Gardiner Hubbard, was influential and later played a role in promoting Bell's inventions. This support allowed Bell to focus on long-term experimentation rather than immediate financial survival. Despite later fame, Bell remained personally modest. He did not cultivate a public persona as an inventor genius. Instead, he viewed his work as practical problem-solving guided by human need. His personal values emphasized usefulness over recognition, collaboration over competition. By the time Bell began intensive work on voice transmission, his character and worldview were firmly shaped. His childhood exposure to speech science, unconventional education, teaching experience, and stable personal life combined to produce a thinker uniquely prepared to challenge existing communication technology. The telephone was not an accidental invention. It was the logical outcome of a life spent studying how humans communicate and how technology could serve that purpose more directly. By the early 1870s, Alexander Graham Bell was deeply engaged in experimental work that bridged acoustics and electricity. His initial objective was not to transmit speech, but to improve telegraphy. At the time, the telegraph was the dominant long-distance communication technology, yet it suffered from a major limitation. A single wire could transmit only one message at a time. Bell became interested in the idea of a harmonic telegraph, a system that could send multiple signals simultaneously over the same wire by using different audio frequencies. This problem aligned naturally with Bell's background in sound. He understood that complex sounds could be broken into component frequencies and recombined. If musical tones could coexist without interference, he reasoned, electrical signals might do the same. Bell's early experiments involved tuning forks, membranes, magnets, and coils, devices that converted sound vibrations into electrical variations and back again. These were not polished laboratory setups, but improvised assemblies built and modified continuously. Crucially, Bell approached these experiments from a physiological perspective rather than a purely electrical one. He thought in terms of vibration, motion, and resonance, not just current and voltage. This perspective allowed him to consider whether the full complexity of the human voice, rather than coded pulses, might be transmitted electrically. At this stage, the idea was speculative and widely considered impractical, but Bell's ongoing experiments kept pushing him closer to the question of speech itself. Bell's experimental progress depended heavily on collaboration. In Boston, he worked closely with Thomas Watson, a skilled machinist and electrical assistant. Watson translated Bell's conceptual ideas into physical devices, machining parts and refining mechanisms. Their working relationship was iterative. Bell proposed ideas, Watson built them, tests revealed flaws, and the designs were revised. Financial support was modest and uncertain. Bell relied on funding from patrons who were more interested in improving telegraph systems than inventing entirely new devices. This constraint shaped his research path. Many of Bell's notebooks from this period reveal a gradual shift from multiplex telegraphy toward direct voice transmission, rather than a single decisive breakthrough. Competition added urgency. Other inventors, most notably Elisha Gray, were working on similar problems involving sound and electricity. Patent law rewarded speed and specificity, increasing pressure to formalize ideas quickly. Bell's work advanced through small, practical steps rather than dramatic leaps. He refined transmitters, experimented with liquid contacts, and tested how varying electrical resistance could represent sound waves. What distinguished Bell during this phase was persistence rather than certainty. Many experiments failed outright. Others worked inconsistently. Instead of abandoning these attempts, Bell documented results meticulously, learning from partial success. This incremental approach allowed him to converge slowly on a workable method for transmitting speech, even as competitors explored alternative designs. The decisive conceptual breakthrough occurred when Bell realized that speech transmission required continuous electrical variation, not intermittent signals. Telegraph systems used on-off pulses. Speech demanded a current that changed smoothly and proportionally with sound vibrations. This insight reframed the entire problem. In March 1876, Bell successfully transmitted intelligible speech electrically for the first time. The famous phrase spoken to Watson was not planned as a demonstration, but emerged during testing. The result confirmed that Bell's approach, using a vibrating diaphragm to modulate electrical current, was viable. Equally critical was the timing of Bell's patent application. Bell filed his telephone patent on February 14, 1876, the same day Elisha Gray submitted a caveat describing a related concept. Bell's application was broader and more detailed, giving it legal strength. This moment would later fuel prolonged legal disputes, but from a technical standpoint, Bell's system was operational and demonstrable. The patent did not describe a finished commercial product, it outlined a method. Bell understood that invention was only the first step. A functional, reliable device suitable for public use still required refinement. Nevertheless, the patent secured Bell's position and allowed further development without immediate fear of duplication. Following the patent, Bell focused on proving the telephone's value. Public demonstrations were essential. At the Centennial International Exhibition in Philadelphia later in 1876, Bell presented the telephone to audiences that included scientists, engineers, and political leaders. Hearing speech transmitted over a wire challenged prevailing assumptions about communication. The reaction was cautious but intrigued. Technical limitations remained. Early telephones were weak, noisy, and limited in range. Bell and his collaborators continued refining transmitters and receivers, improving clarity and amplification. Importantly, Bell did not attempt to control all aspects of commercialization. He allowed others to adapt, improve, and scale the technology. Institutional acceptance followed gradually. Businesses recognized the telephone's potential for real-time coordination. Networks began forming, and infrastructure development accelerated. What had begun as a theoretical extension of sound science became a practical communication system. Bell's journey to the telephone illustrates a disciplined progression rather than a single moment of genius. His success rested on sustained experimentation, interdisciplinary thinking, collaboration, and careful documentation. He did not set out to invent the telephone as a defined goal. Instead, he pursued a deeper understanding of sound and communication, allowing practical invention to emerge from that pursuit. This journey underscores a broader principle of innovation. Transformative technologies often arise when existing problems are re-examined through a different conceptual lens. Bell's telephone was not merely an improvement on telegraphy, it was a redefinition of how human voices could move across distance. The telephone is fundamentally a device for converting sound energy into electrical energy, transmitting that energy across distance and then converting it back into sound. The central technical insight behind Alexander Graham Bell's invention was that the human voice does not need to be encoded into symbols or pulses to travel over a wire. Instead, the shape and intensity of sound waves themselves can be represented by continuous variations in an electrical signal. Human speech consists of pressure waves moving through air. When a person speaks, their vocal cords vibrate, creating complex waveforms that vary in frequency and amplitude. Bell realized that if these vibrations could cause a corresponding variation in electrical current, the signal could carry the full richness of speech rather than simplified codes like Morse. At the transmitting end of an early telephone, a thin diaphragm, usually made of metal or treated parchment, was placed near the speaker's mouth. Sound waves caused this diaphragm to vibrate. These vibrations were mechanically linked to an electrical circuit, allowing sound to directly influence current flow. This was the essential leap: continuous electrical modulation, not binary signaling. Bell's earliest telephone transmitters were simple but conceptually powerful. The vibrating diaphragm was connected to an electromagnet or variable resistance contact. As the diaphragm moved, it altered the magnetic field or electrical resistance in the circuit. These changes caused the electrical current flowing through the wire to fluctuate in precise correspondence with the sound waves. In Bell's original electromagnetic transmitter, the diaphragm was positioned close to an iron armature attached to a magnet coil. When the diaphragm vibrated, it slightly changed the distance between the armature and the magnet, inducing a fluctuating electrical current. Importantly, the current did not switch on and off. It rose and fell smoothly, mirroring the shape of the sound wave. This approach was technically fragile at first. Early transmitters produced weak signals and were sensitive to distance and background noise. Later improvements, such as carbon transmitters developed by other inventors, greatly increased signal strength by exploiting pressure-sensitive resistance. However, Bell's core principle remained unchanged: mechanical motion directly controlling electrical variation. The transmitter thus acted as a translator between physical sound and electrical form, preserving timing, pitch, and intensity. Once the electrical signal entered the wire, it traveled at near the speed of electricity, vastly faster than any physical messenger. The transmission medium, initially simple copper wires, carried these variations over distance without interpreting them. The wire itself did not understand speech, it merely conveyed changing current levels. At the receiving end, the process was reversed. Bell's receiver used an electromagnet positioned near thin diaphragm similar to the transmitter's. As the varying electrical current flowed through the receiver's coil, it caused corresponding changes in the magnetic field. These magnetic fluctuations pulled the diaphragm back and forth, recreating the original vibrations. When the diaphragm vibrated, it pushed against surrounding air molecules, producing sound waves that closely matched the original speech. The listener heard a recognizable voice, not because the system reproduced words symbolically, but because it reproduced the physical waveform of speech. Accuracy depended on several factors: diaphragm sensitivity, magnetic response, wire quality, and electrical losses. Early systems were imperfect, producing faint and distorted sound, yet even limited clarity was revolutionary. For the first time, a human voice could be heard across distance without physical presence. From a technical standpoint, Bell's telephone was not a single component, but a coordinated system: transmitter, transmission medium, and receiver working in harmony. Each part had to function adequately for the system to succeed. Improvements in one area, such as better transmitters, enhanced the entire experience without changing the underlying architecture. The original telephone had clear limitations. It lacked amplification, making long-distance calls difficult. Background noise interfered easily. Early networks required direct point-to-point connections, limiting scalability. These challenges were addressed over time through engineering advances. Switchboards, amplifiers, improved materials, and later electronic components. What made Bell's design enduring was its conceptual robustness. The principle of analog signal transmission, continuous variation representing sound, became the foundation of telecommunications for nearly a century. Even as technologies evolved from analog to digital, the core idea of converting physical phenomena into transmittable electrical representations remained central. Technically, the telephone demonstrated a critical lesson in systems engineering. Complex human information can be transmitted effectively by preserving its physical structure rather than abstracting it prematurely. Bell's work showed that engineering success often comes from aligning technology with natural processes instead of forcing artificial constraints. In summary, the telephone works because it treats sound as motion, motion as electricity, and electricity as motion again. Its elegance lies not in mechanical complexity, but in faithful translation across domains. By grounding his invention in the physics of sound and the realities of human communication, Alexander Graham Bell created not just a device, but a template for modern communication systems, one whose influence extends far beyond the wires of the 19th century.